Dounreay, 1967. This site in the north of Scotland was selected for Britain's first nuclear power station based on the fast breeder reactor principle.
It was conceived as a prototype with an electrical output of 250 megawatts and named the Prototype Fast Reactor, or PFR. Its purpose was to provide experience for the construction of the 1,000 megawatt fast reactors envisaged for the future.
Dounreay was selected because an experimental fast reactor had already been in operation on this site for 8 years. The DFR, as it was called, had proved that liquid metal could be used successfully to extract heat from the reactor core. But some further development work was needed to confirm the design of components on the new reactor.
The heat transfer system adopted was as follows. In the primary circuit, liquid sodium flows continuously between the reactor core and the intermediate heat exchangers. These form a link with the secondary circuit, in which an independent sodium supply picks up heat and delivers it to the steam generators or boilers. The steam produced in the boilers is fed to the turbines, condensed, and returned to the boilers in the usual way.
The building in which the reactor would be situated was erected early in the construction program so that subsequent work associated with the reactor would not be delayed by the weather. The steam generating plant and turbine hall were planned as extensions to this building, forming one single complex. The reactor itself was to be constructed below ground level in a concrete vault in the following way.
Inside the concrete vault is a stainless steel tank. This is surrounded by a leak jacket, both tank and jacket being suspended from the reactor roof, in the center of which is a rotating shield used for the refueling operation. Also suspended from the roof is a support structure for the diagrid and for the reactor jacket, which controls the flow of hot sodium from the core to the intermediate heat exchangers. One of the heat exchangers is shown on the right of the diagram. The flow of sodium back to the core is affected by 3 pumps, and one of these is shown on the left. In plan, the reactor jacket can be seen to contain 6 pods, which house the intermediate heat exchangers, the 3 pumps being situated outside the jacket. Beneath the rotating shield are the guide tubes for the control and shut-off rods, enabling them to be lowered into the core beneath. The core is made up of a large number of containers known as sub-assemblies. The fuel zone itself, shown red, being quite small. The sub-assemblies also contain the depleted uranium breeder material, shown green. This, the reactor will convert into new plutonium fuel. Further breeder material also blankets the fuel in this way, the blanket being surrounded by neutron reflectors, shown yellow. Neutron shielding, shown blue, protecting the intermediate heat exchangers, is provided by rings of graphite-filled steel tubes.
This cutaway model demonstrates the upwards flow of sodium through the hot core, followed by a downwards flow as it gives up its heat, cool sodium being pumped back to the base of the core.
Flow patterns of the sodium inside the reactor were studied using water containing opalescent particles and scaled-down components of the reactor constructed in perspex.
Experience with the DFR had shown that it was essential to avoid gas entrainment within the coolant, and this laboratory work showed how it could be done.
Over 1,000 tons of sodium was required, and it had to be accumulated gradually. The sodium was stored away from the main building complex, and here it was purified. As the turbine condenser was to be cooled by seawater, a pump house was required. This was also sited some distance away, over the intake point on the coast.
Early morning, January the 12th, 1968. On this day, the lower, domed end of the leak jacket which had been prefabricated in a temporary building nearby, was winched out into the daylight for a short but slow journey to the reactor hall. The leak jacket was the first large reactor vessel to be prefabricated in this way. Once the domed end had been brought into the reactor hall, its upper plates could be added until the full height of the vessel had been built up, 42 feet.
After stress relieving at 600 degrees centigrade, the vessel was now ready for transfer into the reactor vault. The leak jacket is only slightly larger than the primary tank, so that if a leak were to occur, the level of the sodium would not drop below the core. Even though the reactor in operation is virtually unpressurized, further safety in the form of secondary containment was provided in the construction of the reactor building. This was clad throughout with precast concrete panels and designed with an acceptably low leak rate. As already stated, the reactor hall was not a separate building, but part of a complex consisting of reactor hall, steam generating plant, and turbine hall, economically sited close together under one roof.
By the autumn of 1968, the empty turbine hall had been completed. The electrical output of the PFR had to be large enough to gain experience on a commercial scale.
To this end, a standard 300 megawatt turbo alternator set was installed. Work was also started on the transmission lines to the south to feed power from Dounreay into the national grid.
In September 1969, the stainless steel primary tank was ready for lowering into the leak jacket. For all these operations, the height of the leak jacket inside the vault was adjusted by the simple process of floating it, then raising or lowering the level of the water. A two-way radio linked the engineer in charge with a survey station in the roof to keep him informed of the exact position of the tank. When fully lowered, it was temporarily suspended from the rim of the leak jacket on hooks.
At about the same time, a works assembly of a dummy reactor core was undertaken. A diagrid supported a honeycomb of hexagonal carriers, each with a central column, designed to accommodate either a control or a shut-off rod. The column serves as a leaning post for the 6 sub-assemblies which surround it, all being tilted slightly inwards to provide stability. The diagrid bearing the reactor core would eventually rest on the diagrid support structure.
This structure was now ready for lowering into a steel framework which had been built to support it, temporarily, above the vault.
The diagrid contains pipes which carry samples of the coolant from each sub-assembly to detectors which give warning if a leak develops in the fuel cladding.
In the background stood the partially completed structure which would constitute the next lift, the reactor jacket. Fabricated sections had been delivered by sea many months earlier, thereby reducing road transport to a minimum.
As the purpose of the reactor jacket was to separate the hotter from the cooler zones of sodium in the pool, thermal insulation was required. Insulation panels were made up of 2 stainless steel sheets with spaces between them, seam welded round the edges and at intervals to form closed pockets of argon gas. After fabrication, every panel was tested for leakage by mass spectrometer. The attachment of these insulation panels to the reactor jacket was carried out in the reactor hall, 4 layers of the panels being applied.
By the summer of 1970, the reactor jacket was ready for lowering into the diagrid support structure. Unlike the other vessels, the jacket was open-ended, and it incorporated 3 compartments, each containing 2 pods, which would later house the heat exchangers. In all lifts, 2 cranes supported a square lifting frame, and remote tilt indicators were employed.
In the meantime, a works assembly of the reactor roof was being undertaken. Later, the main reactor vessels would be suspended from it, and access to all reactor components would be through the roof. The only penetrations on the side of the roof were situated well above the sodium level. These were the ports for the nitrogen coolant and the sodium leak detection equipment. In the center of the roof was the machine surface for the bearing of the rotating shield.
Elsewhere, the rotating shield itself was being fabricated. It was turned on its side to facilitate the machining of the tubes through which the control and shut-off rods would pass. Offload refueling, involving the use of this rotating shield, was effected in the following way.
This simplified diagram shows how the rotating shield, shown blue, carries the refueling machine, a vertical cylinder containing the charge chute. When a sub-assembly, shown yellow and not to scale, is to be withdrawn from the core, the shield must be rotated until the refueling machine is radially in line with the fuel. The charge chute is then extended over the sub-assembly.
In this works test, the charge chute has already been extended, and power is being applied to drive the fuel gripper down through the charge chute.
Above the reactor roof, there is a clear working platform with a circular turntable in the center attached to the rotating shield below. A console is mounted in the turntable, providing the controls for the whole operation.
This console was tested on a temporary rig at Dounreay. Here it is being used to operate the sweep arm, which searches the top of the core for obstructions before refueling. The test rig, which was also used for training operators, enabled the refueling system to be studied outside the reactor.
Under operational conditions, the refueling machine will of course be submerged in liquid sodium. The stage has now been reached for the fuel sub-assembly to be drawn up into the charge chute.
And here, the same operation is being performed on the test rig.
The charge chute has to be retracted again before the fuel can be transferred temporarily to a storage rotor in the primary tank. This involves a further rotation of the shield and a further extension of the chute before the fuel can be finally deposited.
All these operations were rehearsed on the rig.
The dummy fuel sub-assembly was finally deposited in this vertical carrier. The storage rotor in the reactor itself holds 20 such carriers, enabling irradiated fuel to decay inside the reactor before being taken out.
By the spring of 1970, the Dounreay coastline had been transformed. All PFR buildings were now completed, and a separate administration block was connected to the main complex by a covered bridge.
Elsewhere, the steam generating units were being assembled, every tube being water pressure tested at twice its normal working pressure. Automatic welding equipment was installed at the top of the bundle. The evaporators, reheaters and superheaters required for generating steam are basically similar. In all of them, bundles of tubes like these form the vital sodium-steam interface.
The intermediate heat exchangers, in contrast, were works assembled with their tubes horizontal.
These are of the counterflow shell and tube type, the primary sodium entering the tubes at 585 degrees centigrade. Argon-arc automatic welding was used throughout. Correct weld profile was of the greatest importance. All welds were examined on the inside of each tube with an optical instrument. Later, they were radiographed, the film being attached to the outside of the tube. The gamma ray source to expose the film was then inserted inside the tube.
During 1971, the reactor roof had been assembled on the framework above the vault, and the leak jacket, together with other reactor vessels, had been raised and welded to it. In January 1972, the completed assembly, now weighing some 1,500 tons, was lowered in one piece with the aid of a lift slab jacking system.
During lowering, the level of the water in the vault was adjusted to maintain a constant load on the jacking system. 20 jacks were used, each carrying 2 screwed rods to which the load was attached. The system was operated by the controller, care being taken to equalize the load on each jack. Lowering proceeded at ½ an inch per minute, until the roof, with its attachments, was finally seated on the rim of the vault.
The roof was designed with 6 penetrations for the intermediate heat exchangers, which transfer heat into the secondary sodium circuit. These 6 heat exchangers were next installed in the roof.
Before lagging was applied, trace heating elements were attached to the secondary sodium piping. These would come into operation during periods of shutdown. The sodium freezes at 98 degrees centigrade.
The steam generating plant incorporated 3 secondary sodium circuits, any one of which could be shut off independently without closing down the reactor. Beyond the steam generating plant lay the 300 megawatt turbine, now ready for initial commissioning with steam from a temporary oil-fired boiler.
In the control room, a small permanent display is supplemented by the latest cathode ray tube data display system, seen here being tested. Computer-processed data presented in the tube can be wiped out and instantly replaced by any other tabulated readout.
A unique view of the reactor core presented itself during the summer of 1972. At this stage, the surrounding rings of neutron shielding tubes had already been installed as, one by one, dummy sub-assemblies were lowered into their carriers on the diagrid. The final core assembly, with nuclear fuel, took place much later, using the refueling machinery already described.
The fuel for the PFR is manufactured in a very advanced and wholly automated plant. This fuel, consisting of mixed oxides of plutonium and uranium to give the required enrichment, is produced as small sintered pellets, which are loaded into long pins. Each subassembly contains a series of grids to support and locate 325 of these fuel pins. The assembled fuel pins are finally inserted into the locating grids by this machine.
At Dounreay, the last big lift was now undertaken. That of the rotating shield, bearing beneath it the tubular guides for the control and shut-off rods, together with the refueling machine. The whole assembly rotates as one piece during the refueling operation. During the course of 1973, the reactor top was completed, the primary pumps installed, and the primary tank filled with sodium. A temporary heating loop was installed to maintain the sodium in a liquid state. Sodium-potassium alloy was circulated in this loop, which acted like a huge immersion heater.
Beyond the reactor lay the concrete caves for the remote control handling and examination of irradiated samples. The yellow cylinders supported on the outside of the caves are the flasks used for the transfer of the fuel and other sub-assemblies to and from the reactor.
It was on this day that Britain's Prototype Fast Reactor began operating at low nuclear power for the first time.
At this juncture, it had been estimated that the raising of a control rod by 3 millimeters would allow the nuclear reaction to commence.
This event marked the end of the construction period and heralded the beginning of a new era, that of large-scale power production in Britain by fast breeder reactors.